You know that picture of the atom, right? The one you see everywhere? It looks like a tiny little solar system with the nucleus at the center and these little electron planets zipping around it. It's neat. It's tidy. It's the first thing we all learn. But what if I told you that picture is completely, totally wrong?
Yeah, seriously. That whole idea of an electron having a nice, clean, predictable path, it's a fossil. It's from a whole other era of physics. If you really want to understand the world we live in today, you've got to be willing to toss out that old blueprint and step into a reality that is way, way weirder. And honestly, a whole lot more incredible.
So let's back up for a second. Where did we even get this whole planetary idea from in the first place? Well, for that, we have to rewind to the early 20th century, to a time when scientists were trying to figure out the atom using the physics they knew, the physics of the everyday world. So in 1913, this absolute giant of physics, Niels Bohr, comes up with a model that just made sense. It was intuitive. He imagined electrons were locked into these specific circular orbits. You can kind of think of them like lanes on a cosmic racetrack. Each lane is a set distance. Each one has its own fixed energy level. Simple.
And what's so powerful about this model is how certain everything is. It says an electron is right here, on this exact path, with this exact radius. It only gains or loses energy when it makes a clean jump from one lane to another. It's a universe with clear rules and no guesswork. Very comforting.
Now, Bohr's model was a huge leap forward. And for hydrogen, the simplest atom, it worked like a charm. But the moment scientists tried to use it for anything more complex, that neat clockwork picture just started to shatter. It turns out reality is a lot messier than that. I mean, it just completely fell on its face trying to predict how atoms with more than one electron behaved. And even worse, it directly contradicted a radical new idea that was about to shake physics to its very core, a principle that would make the whole idea of a predictable path totally impossible. And this is the final nail in the coffin for the orbit model. The Heisenberg uncertainty principle basically says the universe has a fundamental speed limit on what you can know. You can know where an electron is, or you can know where it's going, but you can never, ever know both with perfect accuracy at the same time. And if you can't know both, the very idea of a defined orbit just dissolves into thin air. And just look how fast this all happened. In just 13 years, in the blink of an eye for science, the entire game changed. In 1926, Erwin Schrödinger comes along and introduces an equation that doesn't treat electrons like tiny balls, but as waves. This was the start of the quantum revolution. So, if electrons aren't zipping around on these tiny racetracks, where in the world are they? Well, quantum mechanics gives us a totally new rulebook. It tells us to stop asking the question, where is the electron, and to start asking a much stranger question. Where is the electron likely to be? The answer to Schrödinger's equation is a mathematical thing called a wave function. Now, this isn't a physical path you can trace. It's a tool, a recipe, that tells you the probability of finding an electron at any given spot around the nucleus. Right here, we've just traded the comforting certainty of the old world for the strange new landscape of probability. And that map of probabilities, that's what we call an orbital. And it's not a line, it's a three-dimensional cloud. It's this fuzzy region where there's, say, a 90% chance of the electron being. But here's the part that really messes with your head. The electron isn't a tiny speck flying around inside this cloud. For all intents and purposes, the electron's wave-like self is smeared out over that whole region. The electron is the cloud. Okay, and this is where it gets really, really cool. Because these probability clouds aren't just random, formless blobs. They have very specific, intricate, and sometimes just beautiful shapes. And those shapes are dictated purely by the mathematics of the universe. The most basic orbital, the one with the lowest energy, is called an s orbital. And its shape? It's a perfect sphere. The math just spits out this beautifully simple shape where the electron's probability is spread out evenly in every direction. But then you add a little more energy, and the math gives you something totally different. The next level up are the p orbitals, and they look like dumbbells, two lobes on opposite sides of the nucleus. And get this, right in the very middle, there is a 0% probability of finding the electron. How weird is that? And it just keeps getting more spectacular. The d orbitals often look like four-leaf clovers, and the f orbitals are even more wild and complex. And I want you to remember, these aren't just artists' drawings. They are visualizations of the real, stable, 3D standing waves that electrons form around a nucleus. It's like the hidden art of reality itself. So let's just lay it all out, side by side. Orbits are the old school, classical idea, a flat 2D path where you know exactly where the electron is. It's deterministic. Orbitals, that's the quantum reality, a fuzzy 3D probability cloud where you can only talk about where the electron might be. It's probabilistic. It is a total and complete shift in how we understand matter. So at this point, you might be thinking, okay, weird shapes, probability clouds, why should I care? Well, this massive leap from orbits to orbitals isn't just some abstract theory for physicists to argue about. It is, and I mean this literally, the foundation of our entire modern world. See, the way these probability clouds, these orbitals, overlap and interact with each other, that is the very definition of a chemical bond. By understanding the specific shapes and energies of these orbitals, we can predict and control how atoms connect. That is the basis of all modern chemistry and material science. Full stop. Just think about it for a second. The computer or the phone you're using to watch this right now, it works because of billions of microscopic switches called transistors. And the behavior of electrons in the silicon of those transistors is governed entirely by orbital theory. Lasers, solar panels, the dream of quantum computing, every single one of those technologies flows directly from our understanding of these strange, beautiful probability clouds. This quote just nails it, doesn't it? This wasn't just fixing a detail in an old model. It was a full-blown revolution in our view of reality. It forced us to abandon the comforting clockwork universe of old and accept one that, at its very heart, is governed by chance and probability. And that leaves us with this huge, profound idea to chew on. The solid, predictable world that you and I experience every single day is built on a foundation of fuzzy, probabilistic uncertainty. If the fundamental building blocks of everything don't even have a definite place to be, what does that really mean about the nature of our reality? That's a question worth thinking about.